So in this video, we're going to talk about what happens when we add multiple slits and what effect does that have on the actual pattern. Okay, so what we mean is I cut a slit into a piece of paper that has a width of 50 micrometers or 0.05 millimeters. And we shine light through that and create a diffraction pattern that looks like this, something that we've seen. That's called single slit diffraction. And then in the last video, we talked about double slit diffraction. So each of these lines has the exact same width, but they're separated by a distance of 150 microns. And it gives us a little bit more complicated of a pattern that looks something like this, that we can calculate using d sine theta equals n lambda, the same formula, except that one gives us constructive and this one's the destructive interference. But what happens when we start to add more slits? So we keep the distance the same, but we just keep adding consecutive slits, 3 slits, 4 slits, 5 slits, 7 slits. What will happen to the pattern? So if we take a look, here I have projected the patterns that are formed on the screen for single slit, double slit, triple slit, quadruple, 5, and 7. And you can see some similarities. Okay, I can see when I'm looking at this that there's a dead zone, okay, a destructive interference zone that stays pretty consistent over here. And I can see that what ends up happening as I start to add slits, I start to make these narrower bands. So instead of this one large band over here, I break it up and I've added other fringes or bands that we call them. Okay, so I have 1, 2, 3, 4, 5 little bands in there. And when I add 3 slits that are separated by the same distance, I narrow those bands down. They're in the same position, but I've narrowed them down. And then I continue to narrow them down as I add more slits. They become more and more narrow. So I can see that the pattern becomes a little bit more complex and then becomes pretty uniform as we go along. But what's interesting is that the original diffraction pattern from a single slit tends to seem to stay all the way throughout. Okay, so this is outlined really well in your textbook, in the SOCOS textbook, and we're just going to talk about it in the video format here. So why does this happen? Why does this pattern develop as we add more slits? Okay, so let's just break it down again. Single slit versus the double slit pattern with the same width. So you can see here I've drawn a barrier that has the same width. Okay, so here's my single slit and here's my double slit. The width of each of these little holes are exactly the same, but in the second one, the spacing between the subsequent hole is 0.15 millimeters as shown above over here. Okay, so if I take a look at single slit diffraction, we remember that diffraction is for the destructive interference, and I can use the formula d sine theta is equal to n lambda to explain that. So then I can calculate this entire diffraction pattern using that formula. And for double slit diffraction, like I talked about in the last video, okay, you would have the same formula, but for constructive interference. All right, so d sine theta equals n lambda for constructive interference. That would be for the first order maxima and the second order maxima. But what we see here is a little complicated pattern that appears. And what is the maxima? What would be the central maxima? Well, this guy right here is my central maxima. That's the center of the central maxima. And then what we would see are these little bands that appear. These are actually the orders, okay? And they got a lot closer together than these orders, all right? And the reason why that happens, okay, so just to highlight that, I'm going to change the color of this so we can see it better. Okay, so that's my central maximum, order, okay? Order. And the reason that they got closer together and a little bit more complicated is because what's really happening is I have 2 single slit diffraction patterns overlapping. So this hole is going to be making that pattern that is going to be over here somewhere. And this hole is also going to be making that pattern that's going to be over here. And they're really close together and they're going to overlap. And this pattern that's formed over here and that pattern that's formed over here, they're going to overlap and constructively or destructively interfere to create this semi-complicated pattern that you see over here. Okay, but the same formula, d sine theta equals n lambda, can be used to calculate all these different patterns. Okay, so that's my single slit pattern, and you see the double slit pattern has quite a lot more complexity to it and a little bit more dots. So if I go back up here, you can see that. That's my single slit pattern. And then the second one is 2 diffractions overlapping from that slit of 50 microns that end up looking like this. Okay, so as we go down, how does that pattern form? Well, exactly what I said. Each of those holes are making a single slit pattern, like that red line that you see here. That's called the single slit envelope. And those two patterns overlap to make a complicated pattern that is shown here by the double slit. Okay, so the single slit envelope would be the original single slit diffraction that would occur through that original hole. And because there's two that are overlapping, they are contained within that and register this double slit pattern that can also be explained by the same formula. Okay, so that's my central maximum. These are the first order maxima, second order maxima, third order maxima, and you start to see them appear lightly over here, come back over there. All right. So what happens when we add more than two slits? So this was the single slit pattern. Here's the double slit where we have our envelope and then a little bit more complex structure underneath it. And then as we add three slits, okay, I added another one. What I notice is that the fringes and four slits, these fringes here start to become narrower. And that's because you keep overlapping diffraction patterns. It's going to get a lot more mathematically complicated to perfectly overlap crests in that position. So these maxima are just the perfect geometry for everything to overlap in that space. It's going to be a lot tighter. Okay, so as we add slits, the fringes become narrower, as you see as we go along. And something else that happens is within the pattern, you start to see these little fringes on the bottom here, okay? And these are the mathematical complexity that would happen by having more than two diffraction patterns. And these little patterns over here, they're called secondary. Okay, so I'm gonna try to use, let's use white. Okay, so these guys over here, the small little blips, are called secondary peaks, okay, or secondary diffraction patterns, secondary maxima, if your textbook calls them that. Those are secondary maxima. And the large peaks are called primary maxima, okay? So the secondary maxima are formed because of the math, the geometry. Things don't quite overlap over there, and so we get these secondary maxima. What I can see, I don't have any secondary maxima for the double slit. They start to appear with the three slit, okay? So I have one secondary maxima in between the peaks. And I can predict how many secondary maxima I have by looking at the number of slits minus 2. So if I had three slits minus 2 is equal to 1 secondary maxima. Okay, and here I have 5 slits, so 5 slits minus 2 is going to be equal to 3 secondary maxima. Sometimes these kind of questions appear on multiple choice on the exam, so it's good to know. I can learn a lot about how many slits I have in my diffraction pattern by counting these secondary maxima. And then the other thing, what you can't see over here, but if I had a plot of intensity, you would see that these peaks grow in height as we go along because the intensity of these peaks depends on the number of slits squared, okay? So if the intensity here at the 5 slit would be 5 times, like 5 squared, so 25 times the intensity of the single slit diffraction pattern. And that makes sense because you're cutting more holes for light to go through, so you should get more intensity in the light. Okay, so go back into your text and read that section and try to just make sense of these patterns, understand what these secondary maxima mean and what happens as we add more slits. Notice that the distance between the peaks stayed the same. And the reason the distance stayed the same is because all these little slits maintain that same spacing. So D is always 150 microns. So in the formula, D sine theta equals n lambda, D is always 150 microns. Okay, it always stays constant, and lambda stays constant. So the angles are all going to be the same, all right? All the angles are going to be the same to the maxima. They're not going to change. The only way I can change the spacing between these maxima is if I change D, the spacing between these slits. So all we're talking about here is what happens to the pattern as I add more slits, but I keep the spacing and the width the same.